Okay. So today I'll talk about Morse theory. So the goal of today would be to look at compact manifolds, something like a sphere or a torus. And what Morse theory will do is it will help us decompose these things into simpler objects. So the sphere will be decomposed as a point and a what I'll call a 2 cell here. So this is nothing but diffeomorphic to a disk in 2 dimensions. Similarly, I will decompose this torus in some other way. So basically that will be the goal for today. And the way this Morse theory will do it is there will be a function and naturally everything shows up. It's not a hands-on construction we do, it comes up naturally. Okay, so first to start with, what is a Morse function? So I will always deal with the n-dimensional closed manifold. And so Morse function will be a function from the manifold to real numbers such that, okay, this has to be smooth, such that if the derivative, if the derivative is 0 for any point P on the manifold, then there exists local, no, there exists. So then the second partials of this function near P, the will form an invertible matrix. So what I mean by this is, suppose x1 to xn are coordinates near P. Then if you look at this matrix, this is invertible. Okay, so wherever you have the first derivative to be 0, you'll want the second derivative to be non-degenerate. And the points where I have the derivative to be 0 are called the critical points. So we define it. Yes, so those will be critical points. Let's look at some examples. So I will only deal with 2 examples throughout this talk. It will be just a sphere. And if you think of this as embedded in R3, you can look at the z values of this function. So this is the height function. So this is R. So you take all values like this. This will be the height function. And this will be an example of a Morse function. This has only 2 critical points, which is the maximum and the minimum. No other point will be critical. And here, if you compute the things, you'll see that the matrix is not degenerate. Other example is for the torus. Again, I look at the height function. Again, here, same thing happens. There are the maximum and minimum will always be critical points. But there are also these 2 saddle points, which are also critical. And yeah, again, the matrix will be non-degenerate here.
Vasu, can you scroll up to the definition once?
Yeah.
Yeah, I hope. Okay. So like the height function, as in you're just taking the z coordinate.
Yeah,
Is
yeah,
that
z coordinate. Yeah,
okay? Thank you.
yeah, yeah. These are embedded inside R3, and this is just the z coordinate. Okay, so now if we have a Morse function, there is a very nice local picture for this Morse function. So that is Morse lemma. Um, okay, let's say the f is a Morse function and c is a critical point. Then near c, there exist coordinates x1 to xn. Such that your function, it will just look like f of c minus so forgetting everything, if you just look at this function, locally you will see 0 is the only critical point. If you think of this on Rn, 0 is the only critical point for this function because the derivative will be just 2xi whatever. And if you take the second derivative, it will just be a diagonal matrix. So this will be a Morse function. And what this lemma is saying is, these are the only kind of Morse functions you have. So every Morse function will locally look like the standard Morse function on Rn. Okay, so for now, every Morse function has a local picture of exactly how it looks near the critical points. Okay, so now, so basically what happens is there are n coordinates and some of them will be negative, some of them will be positive. Okay, that's how it has to be. So now this split of positive and negative, this is independent of coordinate change. If I had taken some other coordinate, this split will always be the same. So k of them will be negative and n minus k of them will be positive. So what I can define is, for any critical point, I can define this k to be its index. So just to tell how many negatives there are. So definition. So k will be defined to be the index of this critical point. So this k split is only associated to the critical point and nothing to the charts. And another corollary of this is, as you saw in this local picture, if c was a critical point, there are no other critical point in a neighborhood of 0. Right? 0 was the only critical point. So which means that all critical points on your manifolds will be discrete. So in a neighborhood of any critical point, there are no other critical points. So critical points will be discrete. And since I was on a compact manifold, it will be finite actually. So corollary is are finite. Proof is locally near C, locally near a critical point. F has the following form. F of x is always like this, plus square. So 0 is the So critical points will be discrete in M, and since M is compact, implies there are only finitely many of them. And so the Morse lemma is proved by, it's an application of the inverse function theorem. You'll just try to cancel off something in the matrices. Okay, so again, going to our examples for the sphere. Was there a question?
Hello.
Yeah.
Yeah. So can you intuitively explain like why this? I mean, this thing will be invertible, the second derivative matrix, for this in the example of the sphere.
Intuitively, how
Uh,
can I?
I mean, or intuitively, like what exactly are we trying to capture with that second derivative matrix?
It is in a way, you are trying to avoid degenerate situations like this. So let's say you take a sphere and you punch it in a little bit, right? So there will be like if you punch this in here, you'll have a ring which is the maximum, right? So your local maximum will be a ring. You are trying to avoid such situations.
Okay.
Okay, so you just want to have one point where the topology changes, sort of.
Okay.
Like locally exactly, like you want to make it this. So like yeah, like the local pictures, if you draw in 2 or 3 dimensions, you either just want a local minima, local maxima, or saddles. You don't want any other kind of thing. Yeah.
Okay. So the local things should be isolated, right? I mean, maxima or minima. That is the idea.
Yeah. The one of the ideas is to make it although this is a consequence, the idea is to make them isolated.
Okay.
Yeah. Yeah, I hope that answers. Okay, so here we had again 2 critical points. One was here and here. And because this was a maximum, it will be 2 negative numbers here because everything else will decrease from here. So the index of that will be 2, index of this will be 0. Again, for this, we had 4, 1 there. So 2 there. This will be index 1 and 1 because these are saddle points. And this will be 0 again. So now how do these critical points relate to topology? So let's take the example of the torus. So let's say, okay, this was a real number. Let's say I start on the negative infinity here and keep going up. And I look at the inverse image of like something like this, like take the whole inverse image of this. So I will look at f inverse of negative infinity to, let's say, some alpha. Right, then I want to see how this changes as I move up. So let's say if let me point out the critical points here. So these were correspondingly here, and here. So if I had taken any point below this, I'll obviously have a empty set. So let's call this alpha 0. So below alpha 0, my set is empty. This is empty. Then between, so now as you go between here, if you look at anything here, let's say, so you'll be looking at everything up to this point, right? So everything here. So it will always look like this. So if I had taken anything above it also, it's just the same thing. It looks exactly like a disk. For any value between here and here, it's always a disk. So between alpha 0 and alpha 1, the set is actually just a disk. And that's the point here. So below this critical point, it was empty. But as I pass the critical point, immediately the topology changes. Again, then between alpha 1 and alpha 2, what happens between alpha 1 and alpha 2? It's something like this, right? This whole thing and this thing. Again, this is no longer a disk. It has two holes. It looks like this. And it looks like this for every value between alpha 1 and alpha 2. If you just move a little higher here, it will still be the same thing, but you just added a little bit extra, which homeomorphic up to homeomorphism, they'll just be the same. Right, then what happens to the final one? Finally, alpha 2 and alpha 3. There it is just, you'll have this whole thing, including the hole. Right, again, the topology is different from what we had. This. And if you go above alpha 3, you'll just have that whole torus. So that's what's happening. These somehow these critical points, as you pass through them, your topology is kind of changing. And in between them, it's always the same. There's no change. Another thing to say is, I guess, if you took two numbers, let's say beta 1 and beta 2, then and if I look at the inverse images, both of them will be circles, and everything in between them is just an interval cross the circle. So it's just this circle cross an interval. Okay, so I guess I'll just write it as a theorem here, which I'll not prove, obviously. So F inverse of, let's say, any beta 1 to beta 2 will be diffeomorphic to F inverse at beta 1 cross an interval.
Is it, you're saying only when they're between the same two critical points?
Yeah, between the same two critical points. So beta 1 is equal to beta 2, and there has to be, it has to be strictly less than the critical points. Okay. Yeah, so topology only changes as you pass through a critical point, and in between critical point, it's the same. There's no change. Okay, so that's one way this kind of captures the topology. There's another.
So can we say what happens at those critical points?
At the critical points, it's a bit. There's some like. So how do you go from this to this, right? What happens is you have to attach these two, like kind of you take 2 points here and you squish, like glue them together. Okay. And similar thing for here to here, it's like you glue these two together and kind of separate them. So some gluing happens, or like gluing or separation, something happens when you go through a critical point. Yeah, but yeah, exactly. This only happens near the critical point. That's the whole thing here. Yeah. Okay. Okay, so I was saying now this was one way I can decompose and we'll see the topology. There's another way which I feel is more useful, which is by doing gradient flows. So gradient flow of F. So now what I'll do is I had the manifold, but now I'll also give a Riemannian metric on this. So Riemannian metric is just a inner product on, okay, let me just write this. So what is a Riemannian metric? So it's for each point in the manifold, GP will just be an inner product. Is so it's an inner product on the tangent space at P. So at each point you have a tangent space, and you just have an inner product, and this inner product is smoothly varying, and GP is so you have a family of inner products on your tangent space. Now, because I have a inner product, because of Rie's representation theorem, what I can do is gives so because of this I can get a unique vector field, which I will call the gradient vector field on M, such that this vector field F, I want it to be the dual of dF. So dF is the differential of F, which I can define without any metric. So this is a one form, or it's in the cotangent bundle. And I will, because I have an inner product, I can get a dual to that, which will be in the tangent bundle. So this was in the cotangent bundle or cotangent space, and I want this to be in the tangent space. So that's why I need a metric here. So because I want to take a dual. Now, this is a vector field, and what this has a property of being the gradient, which we know already. So on Rn, the gradient of F will be nothing but the same thing we know. It'll just be the partial derivatives. And gradient F will also point in the direction of so it will point in the direction of greatest increase, right? That's the property of gradients. Instead of taking F, I will take negative F's because I want to go from top to bottom instead of going from bottom to top. Just a convention people use. So what is the gradient flow? So now let's say we had a circle. Because of the gradient flow, we have a vector field given. Because of the gradient, we have a vector field, which is just, it kind of points like this. Right here, it just goes down. Right, so at each point, you kind of just get a direction of saying how you go to the minimum or how you decrease. What you can do is you can kind of integrate these vector fields to find a path which kind of goes through them. Okay, so you can always do this. So that is what will be called the gradient flow. So basically you will start at a point and you will try to move in the direction the vector field tells you. So that will be called the gradient flow or the vector field flow for this vector field. How do I formulate that? So what is gradient? So it's a curve gamma, let's say from minus epsilon to m, satisfying, oh, this is C infinity, okay. Satisfying, what do I want? I want its initial point to be at P. So you kind of start at P, and you also have to satisfy a differential equation. That is, if you take the derivative of your curve, so basically what you want is derivative is the direction of the velocity. So you want the velocity vector to be pointing in the direction of your gradient vector. So if you had a curve, you want your vector here, it should be pointing in the direction of my gradient, right? That's what I want. So I will say this will be equal to the negative gradient at gamma of T, right? Negative is just for convention. So this is what will define a gradient flow, and any solution to this will be it will be a gradient flow. And again, theorem which I will not prove will be, this is an ODE. ODE, and locally if you put this in charts, it's it will be, you can solve this ODE with because I have a initial point given. So this is an ODE, first order ODE with the initial conditions given. This will give a unique solution. So it has a unique solution. Oh, I should say I gave the initial conditions is given, so it has to have a unique solution. So what it is saying is, given any point, if I have the vector field flow given, there will be just one and only one point, one flow which will go through it. You can't have one going like this and one going like this. There has to be only one of them. And another point I should probably mention is this epsilon can be taken to be all of R. So it can be going, this can go off to infinity. Epsilon can be taken as large as infinity. And exists for infinite time. Okay, so infinite time solutions exist. That is not because it's an ODE, it's because the manifold is compact. Yeah. Also, if note, if you look at the values of your function over your gradient flow, so if you just look at, I have a flow and you look at your values of the function on it, it has to be strictly decreasing. This has to be decreasing, except for when the velocity becomes 0, except for when this gradient vector is 0. And this gradient vector is 0 exactly when its dual was 0. So its dual was the derivative of f. And if df is 0, it means it's a critical point. So this is decreasing except for critical points. at okay. And another thing you can check is whenever you hit a critical point, if you hit a critical point, there is no way you can escape it. You will always just stay there. So if any gradient flow comes and hits it here, it's constant after that. So so after hitting a critical point, so flow okay. Okay, now something which you can see is, you would, I guess, intuitively looking at this picture, or if you look at the other picture, you will see that all of these curves kind of end up going into the critical point. Here, since it's the minimum, it has to go into the critical point. Or in the case of the torus, again, if you look at the flows, they will kind of start and they will either like go like this to here, or they will kind of go down here or here or here. So if you draw a bunch of them, you will observe that all of them tend to end up in critical points. And this in general is a fact. So theorem is that gamma t be any gradient trajectory, then limit as t goes to plus or minus infinity, this exists and is a critical point. So every gradient trajectory will end up going into a critical point. So it will start and end always at critical points. Okay. Okay, so now since they always start and end at critical points, I can ask, given a point, there will be a gradient flow going through it. So given any random point, there will be some gradient flow going through it. I can ask, where does this gradient flow start and end? Because there's a unique one, I can always do that, and this exists for infinite time. So you can always ask what's the source of this gradient flow and what's the sink. So that will be called stable and unstable manifolds. So what's the unstable manifold? Unstable manifold is basically all the sources, or the source to which this critical point belongs to. So this will be, so let's say C was a critical point. So WU of C will be, or maybe I should say it in a better way. So WU of the critical point will be all the points you start your gradient flow at this point, and see what all points you cover as you flow through. So those will all be the points belonging to this this unstable manifold. So all points X and M, such that limit t goes to negative infinity. So take any gradient flow starting at X, this one, this has to be C, where gamma X through X. So,
but Kartik, you said that once a curve reaches a critical point, there is no way of escaping it. So then, like, what does it mean? Like then the car will pass to only one point, right? One physical point.
No, I meant, so what I mean is, it's like, if you are flowing like this and go through this cannot happen. It's like you cannot go to a critical point and come out. If you go to a critical point, you end up at it, or you start from a critical point. So like you can start from a critical point, starting again, because I'm not saying it's at a finite time, it's at actually happening at infinity, right? It's, you are limiting to that. That makes sense. So if you start from here, obviously you'll not flow, you'll just stay there. But what I'm saying is, take something here and see, flow in the reverse direction and see where it goes. Maybe that's a better way to say it. So start somewhere, flow in the reverse direction, and see which critical point you get.
Sure.
Yeah, okay, we can look at some examples. So for the circle, it's pretty simple. You have, so the gradient, we'll give two different colors here. So I'll just denote these two critical points with different colors so that I can show you what the unstable manifold for each is. So if you start at any point except for the bottom one here, you will have flown from the maximum value. So all the flows will look like this, like this, right? Because there's only one maximum. So the unstable manifold for the red one, so the unstable manifold for my red point, it will look like, it will look just like a sphere, except for the bottom point missing. So it's a sphere, except the bottom point is missing. And the unstable manifold of the green point, this will be nothing but just the point. There is, starting from here, you will not flow into any other critical point where there's nothing else below, right? You have to decrease from there. There's no way you can decrease. So the unstable manifold decomposes your space into this thing here and this thing here. And something you can notice is this is homeomorphic to a disk. So this actually looks like a disk, like that. If you just like open disk, maybe, or you can even take it to be Rn. Let's look at the example of torus. Here it gets a bit complicated. So I'll just denote the different critical points by different colors. So now, so what's the unstable manifold for, let's start with the bottommost one, green. Again, green is the minimum. So for this, the unstable manifold will just be the point. Nothing else will flow from it. Now going for unstable manifold of blue. So what are all the things which start and flow from here? It will just be two gradient flows which will flow on these two directions, right? So one will come out and go down, one will go from the back of your torus. Okay, so there will be only two which go through this. So these will be the only two gradient trajectories. So it looks like, it just looks like this, where the bottom point is missing. Similarly for purple. For purple, again, it will just go around this hole. Right. So that will again just be something like this. And for red, this is the most complex one. All these gradient trajectories belong to red. these two, of course, but things like that go through here, and things that go very close to these also, even those belong to it. So in the end, if you write down everything, what happens is you just have to, the only points that it will miss is you will just miss these points and these points. So everything in like purple, blue, and green, those are the only things that will be missing. So it will look like so that is missing, and also this is missing, right? So if I again draw this a little better, it will look like Mr. joint, and the whole thing is here, and basically this boundary is not included, so this is an open set kind of thing. Okay, that boundary is not included, and this will be the thing. And again, you will see that this is basically a disk, open disk. And again, here you see these are also disks, but because they are intervals, they're just disks in one dimension. So what has happened is these unstable manifolds decompose your space into many disks, and the way you attach these disks in some way that will give you your whole manifold. So you have kind of what you have ended up doing is you have given a cell complex structure for this in a very natural way. Okay, some facts. Something you can notice is because red had index 2, the unstable manifold also has dimension 2. Green had this purple had index 1, so this will also be dimension 1. This is 1, this is 1. This had 0, so this is 0.
I think.
Yeah.
So sorry, I forgot. What was the definition of index?
Index is how many negative numbers are there. So you at the Morse function near a critical point will look like minus x squared
okay.
plus x squared. So how many negative there are, that is the index. And and it so happens that index will tell you how the dimension is. Yeah.
And is that like the negative or positive at a point? Like, does it depend like if you're going down or going up? Is that how it?
Yeah, it's just convention. If I took the index to be positive, then I will be looking at stable manifolds instead of unstable manifolds.
No, I think my question was that, like, intuitively, how do you decide the index? Like, for example, what I was thinking was like, from the top view is always going down, so each coordinate like will have like minus x square sort of thing.
Yeah. So
at the centers. So
if you're near like a saddle point here, you will see there is one direction where you decrease to the point, and one direction where you I'm saying this in a reverse way now. I guess I'll draw a picture. So saddle will look like something like this, right? So near a saddle point, you will have something like this. I don't know how to draw a saddle properly, but yeah, near saddle, you will have something which is like U going up and an orthogonal U going down. So that is how you decide. So you will have one direction going up, one direction going down. Okay. So that's how you do. So that will be one negative, one positive. Yeah. Yeah. Okay. So anyway, facts was unstable manifolds of a critical point will be smooth manifolds. Obviously, this requires a proof, but just go with me, saying all these unstable manifolds have to be manifolds of dimension index of C, which is K. And secondly, these manifolds are very simple. These are actually is a K cell. K cell as in it's a ball in RK. So it's a K dimensional open ball, basically. Right. So because we have such a decomposition, this gives a CW decomposition of M. Yeah, so basically you get a CW decomposition. So now this has captured the topology in a way. And whenever you have a CW decomposition, you can compute the homology using the cell complex, the cells you have. So maybe I can do Morse homology a little bit. So this thing that it computes homology is not something related to Morse theory, because we already got a CW decomposition, it will automatically compute the homology. But there is a different way you can look at the homology here, or different way you can look at the complexes. So definition is, let's say A and B, let them be critical points. MBA. So MBA be all points on joining A and okay, B to A, sorry. So you had your sphere, you had your critical points. So MBA will be all the points between A and B. So take trajectories joining B and A. So the top one will be called B. This will be A. Look at all of them joining here and look at all the points it traces out. So that will be the set MBA. Now there is a R action on trajectories. Spelling is wrong, but whatever. Trajectory. So if gamma was a trajectory, I can do an R action by saying, let's say, take alpha dot of gamma of t. I can define this to be gamma of alpha, this plus alpha. So basically, if you had any trajectory starting at this point, I will just say start at this point and take the same trajectory. Okay, so it's just what this is doing is just taking a point here and kind of translating along the trajectory. So this R action also acts on MBA just by doing the same thing. So every point is just mapped to something in its orbit or in the trajectory. So basically the orbits of this action will just be trajectories. And what I will do is I will consider the space LBA, which is nothing but take MBA and mod it out by the quotient it out by this. So for the sphere, since all the trajectories were like this, so if you just quotient out everything going down like this, what you'll be left with is just a circle like this. So what this is counting is it counts each trajectory as a single point. So each trajectory will be counted as a single point. And here is that. Right. So that's what this space is. And again, there's a theorem saying this happened to be a smooth manifold, which is always the case, saying this is smooth manifold of dimension index of B minus index of A minus 1. Okay, so the dimension of this will depend on index of B, index of A, and you just subtract by 1. There is one small technical condition which I'm ignoring here, because if you, without that, if you apply this to the torus case I was doing, this will not work out. This will give you a negative number. So there is a technical condition which has to be applied, but let's ignore that for now. So now what you can look at is, if you look at my goal is to define a chain complex. So a chain complex will be defined like take something from q plus 1 and going to CQ, right? So what is happening here is, what I'll do is, in this chain complex, I'll take all the points of critical point, all the critical points of index q plus 1. Here it will be q. So the indices here differ by 1. And I want to count the number of flows from each of them. Okay, so if index of B was index of A plus 1, so they just differ by index 1. What happens to this formula is this will just become 1 over here, or sorry, it will become 0. So this becomes 0. So the dimension of this manifold which I had defined, so basically counting trajectories, it will be a 0-dimensional manifold. So instead of being like this, it will just be a bunch of points. Okay, 0-dimensional manifolds are just points. And what I can do is I can count the number of points. Okay, so that will be the number of trajectories going from one critical point to the other. Okay, so if this happens, then the dimension of LBA equals 0 implies LBA is a bunch of points this is finite because of, again, something more which has to be said, but let's just take that these are finitely many points. And what I can define is, I can define N of BA to be the cardinality of this L of BA. Okay, for now, let's just assume it's finite. Now that you have this number, I can define my complex which I wanted. So the complex will be defined as CQ is defined to be, what did I define it to be? Okay. CQ is defined to be free Z module generated over critical points of index Q. So take all the critical points of index Q and basically take a free module over this. So every critical point will look like a generator. So any element of this will look like summation some number times C, where C belongs to crit Q. So index q critical points of F, take all of them, and elements of this module will look like this. Right, so that's a free module. And how do I define my boundary map? Boundary map will be defined to be from CQ plus 1 to CQ. If you take any B belonging to, so I'll just define it on the generators. I'll just define it on the generators over here. So let's take a generator B here. What will I want this to be? This will be defined as summation, take every element A in the crit Q of F. This will be N of BA times A. Okay, so that will be an element over here. So this is also technically not correct. But if I had instead taken Z mod 2 here, Z mod 2Z. So I'm just counting numbers modulo 2, yeah. So if you do counting modulo 2, then this actually is well defined, and what you get is this complex CQ minus 1 dot dot dot. This del squared will be 0. Okay, only then this will square to 0. And another thing is the homology of C star will be isomorphic to the homology of M. Okay, that's also a theorem which I will not prove. Okay, cool. I guess I'll just stop here.
Can you go above?
Yeah.
Like where dimension formula was written?
Yeah.
Yeah. So can you do this in the case of